Hi everyone, in this recording we'll be going over zeros of polynomial functions, and our goal is that by the end of this presentation you'll be able to use the fundamental theorem of algebra to count zeros, you'll be able to find rational zeros using the rational zero test, you'll be able to use complex conjugate pairs for polynomials with real coefficients, and you'll be able to find zeros by factoring and division, and use sign rules and bounds to narrow the search. The fundamental theorem of algebra states, if f of x is a polynomial of degree n, where n is greater than 0, then f has at least one zero in the complex number system. This means that every nth degree polynomial function has exactly n zeros in the complex number system, counting multiplicity. The linear factorization theorem states, if f of x is a polynomial of degree n, where n is greater than 0, then f of x has precisely n linear factors. So f of x is equal to an times x minus c1 times x minus c2 all the way to x minus cn. So c1, c2, all the way to cn are complex numbers. So zeros and factors are directly connected. So each zero, ck, corresponds to a linear factor, x minus ck. So here we have some examples for the first one, starting off with the first degree. F of x is equal to negative x minus 2. So this one has exactly one zero at x is equal to 2. For our second degree example, we have f of x is equal to x squared minus 6x plus 9. So we have x minus 3 squared. So this one has exactly two zeros, counting multiplicity, at x is equal to 3 and at x is equal to 3. So this is a repeated zero. Now we have the function f of x is equal to x cubed plus 4x. So this one is of third degree. So we have x times x minus 2y times x plus 2y. So this function has exactly three zeros at x is equal to 0, x is equal to 2y, and at x is equal to negative 2y. So a key takeaway is that a polynomial of degree n has exactly n zeros in the complex number system, counting multiplicity. So the rational zero test states that if a polynomial f of x has integer coefficients, then every rational zero of f has the form p divided by q, where p and q have no common factors other than 1, and p is a factor of the constant term a naught, and q is a factor of the leading coefficient a n. So how do we use it? First, we list the factors of the constant term a naught, then we list the factors of the leading coefficient a n, then we form all simplified fractions, p divided by q, and we test each candidate by substitution. So we plug in p divided by q into our function. So we are given the example to find, if possible, the irrational zeros of f of x is equal to x cubed plus x plus 1. So we identify our coefficients, so a naught is equal to 1, and our leading coefficient a n is equal to 1. So the factors of a naught are 1 and negative 1, and the factors of a n are 1 and negative 1. So all simplified fractions are of the form 1 and negative 1. So lastly, we test by substitution. We test x is equal to 1, so f of 1 gives us 3. That is not equal to 0. Then we test x is equal to negative 1. So f of negative 1 is equal to negative 1, which is not equal to 0. So that means that the polynomial f of x is equal to x cubed plus x plus 1 has no rational zeros. So here's the same example and the same process, just expanded so that it is easier to follow along. In this slide, we are given the function f of x is equal to x to the power 4 minus x cubed plus x squared minus 3x minus 6. We'll be using the rational zero test. So we see that this function has a leading coefficient of 1 and a constant term of negative 6. So the possible rational zeros are factors of the constant term over factors of the leading coefficient. And for this case, our possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So first we test x is equal to negative 1. So we put that on the outside of the box, and on the inside we have our coefficients 1, negative 1, 1, negative 3, and negative 6, and we'll be using synthetic division. So we drop the 1, then we do 1 times negative 1, which will give us negative 1. So negative 1 plus negative 1 gives us negative 2. Negative 2 times negative 1 will give us positive 2, so 1 plus 2 is equal to 3. Negative 1 times 3 will give us negative 3, so negative 3 plus negative 3 is equal to negative 6, and negative 6 times negative 1 gives us positive 6, so negative 6 plus positive 6 is equal to 0. So since we have a remainder of 0, x is equal to negative 1 is a rational zero of our function. Now we repeat the process, but this time with x is equal to 2, and we'll be using synthetic division. And this will be done on the quotient that we just attained. So we put our coefficients, 1 from the x cubed, negative 2 from the x squared, 3 from the 3x, and negative 6, our constant term. And then 2 on the outside since we were testing x is equal to 2. We drop the 1. 1 times 2 is equal to 2, so negative 2 plus 2 is equal to 0. 0 times 2 is equal to 0, so 3 plus 0 will give us 3. And 3 times 2 is equal to 6, so negative 6 plus 6 is equal to 0. So since we have a remainder of 0, x equal to 2 is a rational 0. So our new quotient will be x squared plus 3. So now we can check the remaining quadratic. X squared plus 3 has no rational zeros because the factors of 3 are plus or minus 1 and plus or minus 3, and none of those possibilities make x squared plus 3 equal to 0. So that means that the only rational zeros are x is equal to negative 1 and x is equal to 2. So our final factored form of the function is f of x is equal to x plus 1 times x minus 2 times x squared plus 3. So now we'll be going over complex conjugate pairs. So for polynomials with real coefficients, complex zeros always occur in conjugate pairs. And this happens because when we multiply a complex number by its complex conjugate, this results in a real number. So what is a conjugate pair? This occurs when we have two complex numbers that have the same real part and opposite imaginary parts. So if z is equal to a plus bi, where b is not equal to 0, then its complex conjugate is z bar, which is equal to a minus bi. Now we have some examples. 2 plus 3i. So its complex conjugate will be 2 minus 3i. Now here's the theorem that connects complex conjugate pairs to polynomial functions. So let f be a polynomial function that has real coefficients. If a plus bi, where b is not equal to 0, is a 0 of f, then the complex conjugate a minus bi is also a 0 of f. So it's important to note that this result is true only when the polynomial function has real coefficients. So for example, it will apply to f of x is equal to x squared plus 1, but not to g of x is equal to x minus I. So why does this happen? When a polynomial has real coefficients, substituting a plus bi and taking the conjugate shows that the result must also be 0. So real coefficients preserve conjugate pairs. Graphically, conjugate zeros are symmetric across the real axis in the complex plane. So now we're given an example for finding a polynomial function given the zeros. So we are told to find a fourth degree polynomial function f with real coefficients, knowing that it has negative 1, negative 1, and 3i as zeros. So the first step is to list the zeros, including the conjugate. So we have negative 1 repeated twice. Now for our complex 0, we have 3i, so then its conjugate will be negative 3i. So now we can write f of x using the linear factorization theorem. So f of x will be equal to some constant a times x plus 1 times x plus 1 times x minus 3i times x plus 3i. So now we can use the conjugate product and multiply the x minus 3i times the x plus 3i, and that results in x squared plus 9. So that means that f of x can be written in the form a times x plus 1 squared times x squared plus 9. So now we can expand and further distribute all the terms, and that will result in f of x is equal to some constant a times x to the power 4 plus 2x cubed plus 10x squared plus 18x plus 9. So for simplicity, we let a equal to 1, and now we are left with the function f of x is equal to x to the power 4 plus 2x cubed plus 10x squared plus 18x plus 9. So now we're given another example, but this time we are given a constraint f of 1 is equal to 3. So we are told to find the cubic polynomial function f with real coefficients that has 2 and 1 minus I as zeros, but this time f of 1 is equal to 3. So the first step is list all the zeros. 2, 1 minus I, and since that is a complex number, its complex conjugate will be 1 plus I. Now we rewrite f of x using the linear factorization theorem. So f of x will equal a times x minus 2 times x minus 1 minus I, and times x minus 1 plus I. So now we multiply the conjugate pair, and we should get x squared minus 2x plus 2. So f of x is equal to some constant a times x minus 2 times x squared minus 2x plus 2, and then further distributing the x minus 2 into the x squared minus 2x plus 2, we get f of x is equal to a times x cubed minus 4x squared plus 6x minus 4. So now to find a, we were told f of 1 is equal to 3. So we plug in 1 to our function, and we get that a is equal to negative 3 after solving for it. So now we can plug back in a is equal to negative 3, and we will get the function f of x is equal to negative 3 times x cubed minus 4x squared plus 6x minus 4. So the final form will be negative 3x cubed plus 12x squared minus 18x plus 12. So for polynomials with real coefficients, non-real complex zeros always occur in conjugate pairs, a plus bi and a minus bi. This helps us build polynomial functions and factor them correctly. By the linear factorization theorem, any nth degree polynomial, f of x, can be written as a product of n linear factors over the complex numbers. So that is, f of x is equal to an times x minus c1 times x minus c2 all the way to x minus cn. So if f of x has real coefficients, complex zeros occur in conjugate pairs. Therefore, f of x can also be written as a product of linear and irreducible quadratic factors over the reals. So every polynomial of degree n greater than 0 with real coefficients can be written as a product of linear and quadratic factors with real coefficients, where the quadratic factors have no real zeros. So now we're given an example. F of x is equal to x to the power of 4 minus 3x cubed plus 6x squared plus 2x minus 60. And we are told to find all the zeros of f of x, given that 1 plus 3i is a 0. So now we use the conjugate pair. If we're given 1 plus 3i, then its complex conjugate will be 1 minus 3i, and that will also be a 0. Now we can multiply the conjugate factors, so x minus 1 plus 3i times x minus 1 minus 3i, and that'll result in x squared minus 2x plus 10. Now we can divide f of x by x squared minus 2x plus 10, and we will see that we get x squared minus x minus 6. So now we can factor the quotient to find the other two zeros, which will be x minus 3 times x plus 2. So that means that the final factorization of f of x is equal to x squared minus 2x plus 10 times x minus 3 times x plus 2. So all of our zeros will be easier to locate. So now we set x minus 3 equal to 0, so that will imply x is equal to 3. And now we set x plus 2 equal to 0, and that will imply x is equal to negative 2. So now all four of our zeros are x is equal to 1 plus 3i, x is equal to 1 minus 3i, x is equal to 3, and x is equal to negative 2. And here we have a visual check. We have the function graphed. Now we're given the function f of x is equal to x to the power of 5 plus x cubed plus 2x squared minus 12x plus 8, and we are told to write it as a product of linear factors. So first we use the rational zero theorem, and we see that the possible rational zeros are the factors of 8, our constant term. So that is plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. So now we test all the possible rational zeros using synthetic division. So first we use x is equal to 1 on the original polynomial. So on the outside of the box, we write 1, and on the inside, at the top, you write the coefficients of f of x. So 1, 0, since we have no x to the power of 4 term, 1 for x cubed, 2 for 2x squared, negative 12 for negative 12x, and 8 for our constant term. We drop the 1, so now we have 1 times 1, and that is equal to 1, so 0 plus 1 is equal to 1. Now 1 times 1 is equal to 1, so 1 plus 1 will give us 2. Now 2 times 1 is 2, so 2 plus 2 will give us 4. 4 times 1 is equal to 4, so negative 12 plus 4 is equal to negative 8. Negative 8 times 1 is equal to negative 8, so 8 plus negative 8 is equal to 0. So our quotient is x to the power of 4 plus x cubed plus 2x squared plus 4x minus 8, and we'll have a remainder of 0. So now we can test x is equal to negative 2 on the quotient that we just attained. So on the outside, we put our negative 2, and at the top, we write the coefficients of the quotient. So 1 for the x to the power 4, 1 for the x cubed, 2 for the 2x squared, 4 for the 4x, and negative 8 for the constant term. So we drop the 1, so 1 times negative 2 is negative 2, so 1 plus negative 2 is negative 1. Negative 1 times negative 2 is positive 2, so 2 plus 2 is 4. 4 times negative 2 is negative 8, so 4 plus negative 8 is negative 4. Negative 4 times negative 2 is positive 8, so negative 8 plus 8 is 0. So now our quotient is x cubed minus x squared plus 4x minus 4 with a remainder of 0. So now we can factor that quotient by grouping. So we do x squared times x minus 1 plus 4 times x minus 1. Since we have an x minus 1 in common, we can group those, so it'll be x minus 1 times x squared plus 4. So we see that the complex factor pair comes from x squared plus 4. So that can be further factored into x minus 2y times x plus 2y. And since the coefficients are real, the non-real zeros occur in the conjugate pairs. So that means that our final factorization is f of x is equal to x minus 1 squared times x plus 2 times x minus 2y times x plus 2y. So the factor x minus 1 squared shows that x is equal to 1 is a repeated double zero. So now finally, we can see all the zeros of f of x by setting each of those terms equal to 0. So that means x is equal to 1 with a multiplicity of 2, x is equal to negative 2, x is equal to 2y, and x is equal to negative 2y. So now Descartes' rule of signs is a rule that will help us estimate the possible number of positive and negative real zeros. So the theorem states that the number of positive real zeros of f of x equals the number of sign changes in f of x, or less than that by an even integer. The number of negative real zeros of f of x equals the number of sign changes in f of negative x, or less than that by an even integers. So here we have a note. Zeros of multiplicity k are counted k times. So we'll be going over an example. Determine the possible numbers of positive and negative real zeros of f of x is equal to 3x cubed minus 5x squared plus 6x minus 4. So first we analyze f of x is equal to 3x cubed minus 5x squared plus 6x is minus 4. So we have the term 3x cubed, and that is a positive term since the leading coefficient is positive. Now we have negative 5x squared, so that is negative since we have a negative 5. Now we have 6x, which is positive because we have plus 6. And our constant term is negative, so that means we will have a negative in the sign. So we see that the amount of sign changes are 3 because we go from plus to minus, from 3x cubed to negative 5x squared. Then we go from negative to positive, from negative 5x squared to 6x. Then we go from positive to negative, when we go from 6x to negative 4. So by Descartes' rule of signs, the number of positive real zeros is 3 or 1. The 3 was from the number of sign changes, and the 1 was from the portion that states less than that by an even integer. So the next even integer is 2, so 3 minus 2 would give us 1. So now we test the negative real zeros by analyzing f of negative x. So we'll get f of negative x is equal to negative 3x cubed minus 5x squared minus 6x minus 4. So all of the terms are negative, therefore there are no sign changes. So that means, by Descartes' rule of signs, the number of negative real zeros is 0. So here to the far right, we have the graph of the function, and we see that the graph shows the function actually only has one real zero at x is equal to 1. So to conclude, the possible real zero counts for f of x is equal to 3x cubed minus 5x squared plus 6x minus 4 are either 3 positive and 0 negative, or 1 positive and 0 negative. So here we are given a problem. A candle making kit contains 25 cubic inches of wax and a mold for a square pyramid. The height of the candle is 2 inches less than the side length of the square base. Find the dimensions of the mold. So here we're building a model. So we'll let x be the side length of the square base. So that means the base area, the length times width, will be b is equal to x squared. So x times x. Now the height was 2 inches less than the side length, so that means the height will be equal to x minus 2. And then we know that the volume of the pyramid is equal to 1/3 the base times the height. So now we can set up the equation. We know we have 25 cubic inches of wax, so we set 25 equal to 1/3 of the base times the height. So the base was x squared times the height, x minus 2. So 25 is equal to 1/3 times x squared times x minus 2. So now we can rewrite this as a polynomial. We multiply by 3 on both sides, so that 25 times 3 is equal to 75, and we no longer have a fraction on the right hand side. And then we can distribute the x squared, so we'll have x squared times x is equal to x cubed, and x squared times negative 2 is negative 2x squared. Now we can move the 75 to the right hand side, so we subtract. So now we have x cubed minus 2x squared minus 75 is equal to 0. So now by the rational root theorem, the possible rational solutions are plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, plus or minus 25, and plus or minus 75. So only positive values will make sense for dimensions. So using synthetic division, we'll test x is equal to 5. So we write 5 on the outside of the box, and at the top we'll write the coefficients of the polynomial that we just made. So 1 for the x cubed, negative 2 for negative 2x squared, 0 for the x term, and negative 75 for the constant term. So we drop the 1, so 1 times 5 is equal to 5, so negative 2 plus 5 is equal to 3. 3 times 5 is 15, so 0 plus 15 is 15. 15 times 5 is equal to 75, so negative 75 plus 75 is equal to 0. So our quotient is x squared plus 3x plus 15 with a remainder of 0. So the remaining quadratic is x squared plus 3x plus 15. So using the discriminant, b squared minus 4ac, we see that our b is 3, so 3 squared is 9, our a is 1, and our c is 15. So 4 times 1 times 15 is 60. So we'll get a discriminant of 9 minus 60, which is equal to negative 51, and that is less than 0. So that means our discriminant will, our quotient will have no real solutions. So we cannot further factor our quotient because our only real 0 was x is equal to 5. So that means we can plug in x is equal to 5, and we'll see that the base is 5 times 5, which is 25, and the height is 5 minus 2, which is 3 inches. So the final dimensions are the base of 5 inches by 5 inches and a height of 3 inches.